Okay, so today we've got two sort of mini topics. It's two topics for the same low price. It's not that low, but we talk about ternary transformations first. Let's say you look at your data with exploratory data analysis, which I encourage you always to do. And you clearly see there's a difference there. Right? And this is something I go through with my honor students every year. We look at the data before we analyze it. We say, let's just look at it. Do we see a difference here or not? Is it the difference we expect or not? And then we go, and I say, go do the analysis of variance and see what happens. They come back to my office and say, I got an F of 1.1. And I go, what? Wonder why that is. That's pretty weird, because it looks like there should be a difference there. It could be. Now, it could also be that there really isn't anything there. But it could be there's a violation of an assumption. And the assumption violation is almost always, that we can deal with, is the assumption, violation of the assumption of homogeneity of variance. It's usually that the variances are way too different from each other. One of the things I ask my students, and I'm noted as the guy in the department whenever the students do their practice thesis talks, I'm the guy going, where are your error bars? Where are your error bars? It becomes almost a running joke. In fact, someone posted on my Facebook feed today a picture of somebody, a cartoon, an XKCD cartoon without error bars. That's how much I'm known for that, which is sad. That's what I'm known for. I love error bars. And I did an experiment years ago, and I gave it to a student to read, and she said, there's no error bars on your graphs. I got you. And I said, then you don't have their counts. No error bars. So I won again. So a lot of times it's because your variances are really different. So you might see something in, like you might have, let's say we have graphs that look like this. Say, well, that's group 2 and that's group 1. Well, group 2 is different from group 1. But what if the error, so let's say this is standard deviation. I know let's make it way bigger. Now you can see why you might not get a significant difference, right? Because the errors overlap. The standard deviations, that's what those would be in this case. We're going to use standard error, which is the standard deviation by the number of square root of the number of means such and sort. That might look, you can see how that could look different, but it isn't. Yes? So the problem that you're running into is you're violating the assumption of homogeneity of variance, which is a real problem. The bigger problem here is a lot of people stop at this point and go, shit, my experiment didn't work. And actually, your experiment looks like it worked. It looks like your units are the problem. Right? It looks like how you're doing the measuring is the issue, not experimental design or your hypotheses. Like that transition? Pretty cool, right? So what can be done? Or as Lenin once said, what is to be done? Some of these are clearly just for me. We can transform our data through some sort of mathematical operation. You can think of this kind of like, we talked about transformations the other day, quite a few times. Think about this. It's kind of like if I was to grade you guys on a curve, which I don't do. I would have some formula, and I would put your scores in, and it would change your scores. Right? It's just a mathematical operation. You will often hear people say, don't do that, it's not fair. And the response I always have is the same. Here's a transformation for you. Let's see, multiply times 5/9 and subtract 32. That sounds crazy. Does anybody recognize what that actually is? Turn Fahrenheit into Celsius. That's all I did there. Multiply times 1.28. I turned Canadian dollars into American dollars. Oh, that sounds like a pretty good exchange rate. Remember for a brief time when it was 1 to 1? There was even a brief time, like, our dollars were a cent more. It was the greatest time. It was a wonderful time. Times are simpler now. You could buy things online and go, I know what the price is. I don't have to do any arithmetic in my head. I have to get a calculator. So it's actually completely fair. It is so. I'm just restating something in different units. That's all you're doing when you're doing a transformation. But the cool thing is, it can fix some of these variance issues. Okay? So you see that what we're going to do here, we're going to show you a bunch of sort of rules of thumb when to use different transformations. Okay? So I'm just re-expressing things, changing things into different units. So here's the first one, the log transformation. I'm taking the logarithm of a number. Does everybody remember logarithms from high school? No, you don't. Okay, so let's, instead of using natural log, which you normally use, let's use log base 10. Just to remind you of 10 is 1, log of 100 is 2, log of 3, etc. Now I'm doing this at the base 10, so 10 to the 1, right, 10 to the 1 equals 10. 10 to the 10 squared is 100. 10 cubed is 1,000. 10 to the 0th power is 1. You're going, excuse me? You learned that in high school, you forgot it. It's a weird thing. So all you're doing is taking the logarithm. Now this is log base 10. You don't actually usually use the base 10 log. You usually use the natural log, which is the base of E. Remember that where E showed up early on when I talked about the function of the normal distribution. It's basically 2.71828. It's a mathematical constant. And you'll see on your calculator there's a button that says ln. That's log, natural log. Okay? So that's usually what you use. Usually use base 10. But what this is going to do is it's going to pull down really big numbers a lot more than it does smaller numbers. And there are a lot of things with logarithmic scales. Decibels are a logarithmic scale. The Richter scale for earthquakes is a logarithmic scale. Right? So if you've been in, we had here once about a 4.5 about 10 years ago. And then you hear there's a 5.5 somewhere, and you go, well, that's only one more. No, that's 10 times more than you had. Because it's a logarithmic scale. Or say 100 decibels is 10 times louder than 90 decibels. Right? 140 will puncture your eardrums. 130 is really loud on your headphones. So 140 is what you hear working outside with around jet engines. That's why they were ear protection. So we have logarithmic things. Nature's full of logarithmic relationships. There's nothing wrong with doing this. If you have an exponential curve, something like reaction time and fatigue. So people, as they're doing a reaction time experiment, get fatigued. Or people, let's say we're giving them a drug. We're giving alcohol. Your reaction time goes up and it goes up exponentially. It eventually gets to a point where you don't react at all because you're aesthetic. But even if you've had like 6 or 7 drinks compared to 2 or 3, it's not like it's just doubled. It goes up exponentially. Well, if it's doing that, let's just make that a straight line. That's all a logarithm does. Now, as a problem, if you've got a scale that has negative values, you can't take a logarithm of a negative number. Well, you can. It's just undefined. So all you do in that case is just add a constant and then take the log. Okay, so it's not hard to do. That's an easy fix. So you go log of x plus k. And k is a constant. So let's say you've got numbers less, let's say your lowest number is minus 5. Let's add 6 to all the numbers, then take the log. That's fine. But it's when you look at something and go, whoa, I got a curve that looks like that. Oh, let's make it a straight line. We like straight lines. We like straight lines. Okay, questions about the logarithmic transformation? Okay, square root transformation. This is used with counted data. So how many are in this group and how many are in this group? Or how many visits to a bird feeder and how many visits to this bird feeder were there? Right? So how many visits were there to this one? How many visits to this one? And how many visits to this one? I'm doing stuff like that right now. Well, actually, people are getting my pay. I'm doing it closer. So far, we've discovered birds don't like it at -30. That's our big, I think I told you guys this, our big discovery so far is birds hate really cold. They just sit there and go, it's so cold, and they don't go for it. They do very quickly. We'll probably end up using this transformation. It's counted data, it's just number of times they show up at different bird feeders. Okay? What happens with counted data, and I don't want to go through the arithmetic behind this, math behind this, but means end up proportional to their variances. So the bigger the mean, the bigger the variance. And you can actually, if you graph it out, you get a straight line between means and variances. You actually want similar variances, right? So what square roots do is they actually fix this. Take the square root of the original number, or add a constant first. Again, let's say you've got negative numbers, right? Or you want to always have numbers bigger than 1, probably, right? Because maybe you have something really small, less than 0, then you get some huge number. So let's add, again, let's say your lowest number is -5, add 6 to all of it. So you take the square root of x plus k, and k in that case would be 6, and that fixes it with counted data right away. It's amazing what happens. What if you just hook the reciprocal of the number? So if the value is 4, now it's a quarter. If it's a fifth, now it's 5. This actually makes the range smaller, so it makes all the variances smaller. This is especially true, let's say you've got values that are all 1 or greater. If you're taking the reciprocal of all of those, now they're all between 0 and 1. This is done a lot with latencies. Because think about it, latency is just the time to respond or time to finish a task. That's just speed. Speed is really just the reciprocal of latency, and then you got some constant, so meters per second or something. So this is what you use this a lot with latencies. In fact, it's almost done all the time with latencies. It's easier for people to understand that than it is to understand, this isn't one you have to explain, let's put it that way. You're just turning time into speed. And when I was in grad school, and we got a lecture like this, we were actually given real data of latencies of rats to run down a maze. And there was nothing there. Except you could see there was something there. And if you took the reciprocal, it just worked beautifully. And they're real data, which is great. Now it gets a little bit weird because you have to take the arcsine of something. And this is something you probably haven't done trigonometry in a long time. So, with proportions or percentages, weird things happen. And you can understand why weird things happen because it's more common to get proportions that are, in the middle between, let's say, 0.35 and 0.65, then it is to get 1.0 or 0.0, right? In a group, because of variance. So you're going to get you get this fat thing in the middle and then thin on the sides. And the two extremes and fat in the middle. So if you've got variances that look like that, it's almost always because you have proportions or percentages. What this does is it stretches both tails out, and if you stretch it all out, make that fat part gets thinner, basically. Think of it that way. And it's actually not quite the arcsine. You take the square root of the value, and then you take the arcsine of the square root, and you multiply that times 2. And why? It's because I said so. Okay. I mean, I don't, look, the trigonometry behind this isn't going to help anybody. But when people say they do an arcsine transformation, that's what they do. And this, I have a real case of this happening. My honors student in 2007, Shauna, was doing really cool work. She collected all these data, we looked at it, and she got very angry, and she swore a lot because this is why we got along, by the way. Literally, her honors thesis was about swearing. It was so funny that she got up to say in her honors thesis talk. So this group heard someone say, "Fuck off." It's the greatest thing. Because it's science, so she had to say fuck for science. And we looked at it and said, "Hey, it worked." And then she went and did it, and it didn't work. And I said, "They're proportions, Sean. What do you do with proportions?" She said, "I don't know." I said, "You're my TA for 3256. You're supposed to know this." I said, 2 times Arcsine square root. I don't know how to do that. And I asked her why I was writing her letters of recommendation for graduate school. Sean is a PhD. I asked her why she was my TA, why she was my student. I questioned her existence generally. But then we quickly did it, and it worked! It fixed everything. Suddenly, it wasn't F is 1.3, it was like 7.9. Look, work, done. And then I told her she should have paid more attention in school. And she said, "I got a 90, I didn't have to pay that much attention." And I told her, throwing her words back at her, "Shut up, I fucking hate you." So, you ever see on Facebook, you see her commenting on things, it always starts with her saying that. People who don't know us are like, "What's going on with that person?" No, that's a term of endearment we use with each other. So this works and it's beautiful. I literally suggested this about a paper 3 weeks ago that I was reviewing for ANOVA. I said, "You know why this probably didn't work? Do this." So a person might take my advice, I'm not sure. Question, when do you transform? Not always. It makes everything more confusing. It makes everything more confusing because when I show you a graph of proportions of percentages, you get percentages. 100% is correct because everybody's right. 50% to alternatives, that's a chance. I don't know what 2 times the Arcsine square root of 50 is, or 0.5. I just don't know. So you never present graphs of transform data. Sometimes you might use a logarithmic scale, that's about it. You typically don't do that. You present the original data and you transform, and you tell the reader you transform it, obviously, in the text. If the variances are messy, you can use the rules of thumb that I've got here and pick a transformation. Okay? If your data do not violate assumptions, it's not like, "Oh man, the variances are all the same, but if I do enough mathematical things, maybe I'll find something." No, that's not how it works. This isn't a method of torture. This isn't like, what I'm going to do is torture the data until it tells me what I want it to tell me. Like, it's not waterboarding it. What you're trying to do here is you're trying to see, do I want to use different units? That's what you're trying to do. So questions on that? So that's part 1 of today's exciting lecture.